Log on, tune in, find out. Another good idea from Cambridge.
Yeah, I want to talk today about how we can infer macroevolutionary processes from phylogenetic trees, and in particular, I want to look at can we infer changes in diversification rates, so changes in speciation and extinction rates over time. And I want to thank Wim and Arne this morning. They gave a great introduction on those kind of issues, so that helps a lot. So the basis on how I do this methods is that, well, we see species phylogenies and they evolved under some macroevolutionary process, and so from the shape of those species phylogenies and the branch lengths, we may hope to also recover this underlying process under which they evolved. And here we see a phylogeny on the mammalian families, and for example, what we can ask is, based on such a phylogeny, can we actually test if the diversification rates in mammals increased following the extinction of the dinosaurs, which a lot of paleontologists suggest based on their fossil data. And so I want to now present to you a method where we can actually test those hypotheses based on trees. And in the following, always when I talk about diversification, I want to point out, I mean speciation minus extinction, so the net growth of diversity. And I'm not the first one looking at such, trying to infer changes in speciation and extinction rates. I think it all goes back to Shawnee in '94, where he presented a method where we can estimate, as Wim said this morning, constant rates of speciation extinction. And in the paper, he has some integral equations involving an integral, which actually account for changes in rates. However, those integrals are hard to solve numerically, and for large trees, it was apparently not possible. Then, when Olaf Belinda Emmett published his mammalian phylogeny, they actually also wanted to address this question: did mammalian diversification rates increase following the extinction of dinosaurs? And so what they did is they looked at the lineage to time plot, which was introduced also this morning. And the idea is, so in a lineage to time plot, we plot time against the number of lineages on a log scale. And if we have constant rate of speciation, so constant lambda, I also denote it by lambda, and a constant rate of extinction, mu, then first we have a slope in the lineage to time plot, a constant, well, we have a constant a line, which with slope lambda minus mu. And towards the present, there's this so-called pull-off the present effect, and the slope goes towards lambda. And now the basic idea in their paper was, well, we look at the mammalian lineage to time plot and check if there were deviations from a constant slope lambda minus mu, and if so, we can detect that as a change in diversification rates. There's one slight problem with it. So now, say we have 220 time steps, and now the rates changed from lambda and mu to another rate where we have no extinction anymore, but just pure birth. So then the lineage to time plot just goes as a straight line until today, so today would be 300 time units. If we now ask when did the slope in this lineage to time plot as we observe it today, now it's 300, when did it change? We actually see 2 points where it changed, where this pull-off the present effect started and when the rates actually changed. But what we want to infer is only a change, well, when it actually happened. So the method can get slightly confused if we have high rates of extinction. Then Rabowski then thought, well, we want to have a full likelihood approach. So we want to calculate those rates, speciation extinction rates, based on a likelihood function. And he introduced a framework where he allowed for one shift in rates. So say we could have had, or we had a change in rates here. However, what he had to assume was that the ancestral interval was independent from the, well, later interval. And this is only the case if we do not have extinction close to the present, because otherwise extinction will change the lineage to time plot in the past. So the method only works if no extinction is present. And so I started thinking, can we have a likelihood approach where we actually don't have to restrict ourselves to have a case of no extinction in a later period? And so for that, we'll now first define a macroevolutionary model where we allow for changes in rates, so that's easy. The harder part will be to derive the likelihood function, so derive the probability of a tree given a certain parameter combination. And then we can use a reconstructed empirical phylogeny and ask which parameters actually maximize this likelihood function, and those will be our maximum likelihood speciation and extinction rate estimates, together with times. And so I put this method into R and simulated trees to see if it actually works. And so in the second part of the talk, I'll show you then the results on this mammalian phylogeny. Okay, so macroevolutionary model with rate shifts. This is not what I independently came up. People simulated under such models. It's rather simple. We assume, well, today is the present, and in the most recent past, we had a constant speciation rate lambda naught and a constant extinction rate mu naught. At time t1 in the past, those rates actually changed to lambda 1 and mu 1. And another couple million years ago, at time t2, they might have changed again. Okay, and so then when we just look how did this macroevolution process happen, we start maybe here with the first initial species. Then speciation events are those branching events, and extinction events are those lineages which just stop. And in this example, we would have 5 surviving species, 5 extant species. And then if this would be a real macroevolutionary process, what we would reconstruct would be the so-called reconstructed tree, where we eliminate all the extinct lineages. And now, this elimination of the extinct lineages now makes this likelihood computation, so the probability of the tree, more complex, because we basically have to integrate over all those extinct scenarios which could have happened and lead to this reconstructed tree. I want to give you a brief idea how we can calculate such a likelihood. Basically, it can be calculated by a recursion. So the likelihood of the whole tree is basically, we have here a speciation event which occurs with rate lambda 2, since we're in this first interval. Then we have the probability density for those two edges descending this first speciation event. And then we need to multiply this with the probability density of the two subtrees. And so this is the recursive part. We have here the probability density of the tree, and back here. So it remains to calculate the probability densities of observing such edges. And this can be done using a differential equation approach. And namely, we need to define a function, p of t, which is the probability density that a certain individual at time t, so this guy here, produced the edge as we see it below t, so this little bit of a blue edge. And so then p of x1 would be the probability density of the whole edge, and p of s would be the initial condition, well, we just have one individual, which is at time s, so that has initial value 1. And now in order to calculate p of t with a differential equation, we need one further function, which is q of t, the probability that an individual at time t doesn't produce any surviving offspring. So it dies. All the descendants are extinct. Then this is the so-called master equation. We can ask, so what is the probability, what is this p at time t plus delta t? So up here. Well, that's the probability that nothing happens in the little time step delta t, and this is 1 minus something will happen, times p of t, the probability that we get the edge. Alternatively, something also could happen, namely a speciation event. But then, one of the two descending lineages must go extinct, and that's where we need this q of t. So then we have one lineage dying, q with probability q of t, and one lineage producing the edge with probability density p of t. And then those delta t square account for scenarios where we have more than one speciation event in this little time step delta t. but we don't need to specify it because now when we let this delta t go to 0, we get a differential equation. And in a similar way, we can also calculate q of t with such, or derive a differential equation for q of t with that approach. And luckily, those differential equations are of a form where they can be solved analytically. And so we get a closed form solution for the probability density of a given tree, given parameters lambda 1, lambda 2, lambda 3, and so on. Now we can use an empirical phylogeny or a simulated phylogeny, put it into this equation, and maximize over all our parameters, so all the speciation and extinction rates, to estimate the maximum likelihood parameters. And we can do that by specifying first 0 shifts in speciation rates, 1 shift, 2 shifts, 3 shifts, and all those different models are nested, so k shifts is nested within a model of k plus 1 shifts, so we can use likelihood ratio tests in order to determine the most supported number of shifts. And this is implemented in a package I call it TreePar, it wasn't very creative. And so one can use a empirical phylogenic tree, estimate the rates. And so I used Olaf Geninda Emmer's mammalian phylogeny because it's very large. It has 4,500 species. It's basically complete on the species level of mammals. And in particular, I was interested, as mentioned before, did the diversification rates change following the extinction of dinosaurs? And so here are the results. So I used this big phylogenetic tree on 4,500 species, and we see here in dark blue the diversification rate estimates, so speciation minus extinction, and in light blue we see the turnover, meaning it's extinction divided by speciation. And we don't see anything at 65 million years ago, so no significant increase in rates. However, we see a peak in diversification rates around 30 million years ago, and then a recent decline in diversification rates. The turnover seems to be, so first of all, turnover can, and people before realized that cannot be estimated as accurate as diversification rates. However, it seemed to be rather low, so the 95 confidence intervals are here up to 0.12. So the first question I then was asking was, how reliable is now actually such an estimate? So I simulated trees of the same size as the mammalian phylogeny, so 4,500 tips, using the parameters which are estimated here. And now the black lines are the re-estimated parameters, so it fits quite nicely. The second thing I did was I wanted to see how do the different mammalian subgroups actually, how do they evolve. And so now here, this blue line is again the whole mammalian tree. And we see that, there's noise, but there's a general tendency to follow this blue line. And in particular, the marsupials, rodents, and whales, the dark levels were the whales, they in particular contribute to this increase in rates at about 30 million years ago, while then other subgroups had some peaks in rates later on, and all but the primates showed a recent decrease in diversification rates. So I was then just browsing a little bit in the literature what was actually happening 30 million years ago. And apparently the climate, it cooled down. So before it was warmer, and until today now we have a cooler climate, and grassland expanded. So this peak coincides with those two events. I'm not suggesting that we can now draw the conclusion this is correlated, but possibly by analyzing other data sets and grasses and concentrating on herbivores, we can check if climate changes or cooling has something to do, the grassland expansion has something to do with this peak here. I then did more, so this was basically the data I analyzed. I then more asked into the direction how robust is the method. I showed you this first result, diversification rates can be estimated accurately. So this plot with those black lines where I simulate phylogenies. For large trees, so in the high hundreds to thousands, also a low turnover can be distinguished from a high turnover, so extinction divided by speciation. However, we cannot pinpoint down the 95 confidence intervals to a very confined interval, but we can say are they 0.1 or 0.9 at turnover? Further, so in a lot of those large phylogenetic trees, we have a lot of polytomies, so unresolved nodes, and the method treats them as being, the method needs a binary tree, but then the binary tree I get by just making it binary but having 0 edge lengths. It doesn't depend on which binary resolution I do. And so I check if, when I simulate trees and then just randomly collapse the binary speciation events to polytomies, does this really bias my results? And fortunately it doesn't. The confidence intervals get larger because I introduce noise into the tree, but the rates can still be estimated. Last I asked, well, so we didn't find a rate change at the KT boundary, which actually also agreed with what Olaf found. I was wondering, does the method actually has the power to detect something? Maybe it's biased to detect only the recent rate shifts. But it turned out, using simulations with different values where we introduce a rate shift at the KT boundary, we can actually detect it. So there seems to be really the power to detect ancient diversification rate shifts. So based on this phylogeny, we just don't have signal, or we don't see a shift, so maybe possibly there was no diversification rate shift. So now a couple more things about the methodology. It can also be used for estimating mass extinction events. So instead now of shifting rates at those time points T2 and T1, we can also say, well, allow for at time T2 a mass extinction event which deletes a fraction rho, say rho 2 of all the then extant species and just continues with the fraction of surviving species. So those would be the ones deleted to this mass extinction event. And then this is also implemented, so one can specify this option. I want to see if in my phylogenetic tree I had some mass extinction events. And simulations showed also that they can actually be recovered if they were severe enough, not if they were just species going extinct. Last, I want to make a comment about accounting for missing species. So fortunately in Olaf's tree, I didn't have missing species, so I didn't have to worry too much about this. But in general, most empirical phylogenies are incomplete, and the method so far accounts for random sampling. So if we know we miss, say, 50% of all the species, if we are happy to assume that species are sampled uniformly at random from the whole set, so this would be, for example, those 4 species, the reconstructed tree then would look like this, because those are not sampled. Then we can apply the method. However, I guess a lot of the sampling procedures are biased in a sense that it's a little bit going into the direction of what Anja was talking about, to maximize diversity. So people go out in the field and want to collect rather different species. And so we investigated. This was then done under constant speciation extinction rates, so it can't do the rate shifts yet. How can we estimate speciation extinction rates when we pick species such that the diversity in a tree is maximized? So here, for example, we would take from each clade below this red dashed line 1 species. And then, we provided a likelihood function for calculating speciation extinction rates, now constant though. And so one generalization will be that to also allow for this biased sampling and rate changes through time. The second generalization would be, we not only know that we sample species such that we maximize diversity, but we also know the size of the clade which each of the sampled species represent. And that might be if we sample 1 species per genera, we know how large the genera are, but we only have the phylogenetic resolution up to the genera. And there again, under constant speciation extinction rates, we estimated the rates, but one extension would be to also allow for shifts. And those 2 extensions actually often resolve, or for some data resolve this paradox that when people estimate speciation extinction rates, often extinction is estimated to be 0, although we know there are a lot of fossils and we know there was extinction. But method, if we sample in simulations, biased, so in that sense, and then assume though in the method to recover those rates, we had random sampling, we get zero extinction, even though in the simulation we put positive extinction. So the sampling might solve some of those this paradox of always estimating zero extinction rates. And this brings me to the end. So just a brief outlook. So Shawnee, or well, first pass and outlook, Shawnee introduced this first concept of estimating speciation extinction rates. And now we extended it to changes in speciation extinction rates and incomplete sampling. And I think what will be very interesting is to look at density-dependent speciation rates. So now speciation rates would not be anymore a function of time, but of the number of species around. And so the more species we have, the lower is the speciation rate. Also, we want to include fossil information, and this is also relevant for looking at viruses, where we have sequentially sampled data, which can be looked at as fossils. And thanks for your attention.
Questions? Olaf, Arne?
I'm still wondering how you went about dealing with the polytomies. I mean, we never went past 50 million years because the tree becomes so unresolved that a lot of the date estimates become really dodgy. And it sounded like you randomly resolved the tree and gave the edges zero length. Is that right?
Yes. So basically, well, we know it's noise. So we know the process, the underlying process would have been a binary bifurcating tree. And so what I did was, in the method, it only can deal with bifurcating trees. So yeah, I say it's just zero edge lengths, and then we have no idea how well this performs. It's for sure some approximation. So I then simulated and then collapsed different speciation events. Like if there were 3 speciation events at 10, 5, and 2 million, I just put them all to the same level, and then ask how well does the method perform.
Isn't that going to give you an artifact simply because you're going to make all the lineages as old as they possibly can? So this bump at 30 million years, could it not, because the rodents are very unresolved about that point. So all of a sudden you're making all the lineages as old as they possibly can. They're all going to come into existence around 30 million years, and it's going to spike the rate.
So you're saying most of the polytomies are around 30 million years?
I'd
No.
have to look at it.
Were speciation events up to very recent times.
There's a huge polytomy in the rodents. It's someplace between 50 and 20 million years, I don't know. And the rodents are half of all the mammals. So that could be the cause of that bump that you see.
So I mean, I collapsed as many branches as I saw in your tree that they're polytomies, but maybe we can talk later, like if you know how it's biased towards which polytomies. I just randomly collapsed, so maybe there would be something to do better.
So can I just ask a simpler, or not simpler, the same question? So if you take a Yule tree with a constant rate, and you collapse everything down so it's a star phylogeny at the root, and you run it through your program, you don't pick up any changes in diversification?
No, if you collapse that much, you wouldn't. Yeah.
You would not, yeah, exactly.
You would not, no. No.
But that's what you want. That's what you'd want.
Well, I think there's no hope if you introduce so much noise that you don't see any phylogenetic tree anymore.
Okay, sorry.
I
So
think
you have two branches, you have a Yule tree, and you collapse the 2 first breaks down completely, so that the only 2 nodes in the tree are deep in the tree. It's under a constant rate model. Would you pick up a change in rates?
If it's just 2 plates, I also think you don't have a chance. So, okay, I mean, one has to, I guess, look with simulation. So I just introduced as much polytomies as which I saw in the data.
Every time you introduced a polytomy, you brought it back to the deepest. You didn't take
no,
the average.
I randomly collapsed them. So deepest would also be.
Okay. More questions? Yes.
It's kind of related that if your simulations are about collapsing polytomies at random, could you get a bias if you collapse small branches more often than large branches? I think that's what real data is likely to do.
Collapse small branches.
Short branch.
Yeah, short branches. You might get a bias. I'm not sure how severe it is. Yes. So I just collapsed randomly.
Yeah, no.
Okay, if there are no more questions, then let's thank the speaker for